Welcome back. We're going to continue our discussion on elimination reactions. Now, the cool thing about the elimination reactions is, except for one major difference, is with all elimination reactions, you result in the formation of a double bond. Now, with substitution reactions, you will not form a double bond at the end of the reaction, whereas with all elimination reactions, you will result in the formation of a double bond. Good. Now, with that said, E2 elimination reactions, E stands for elimination. E2 is very similar to SN2, and E1 shares a lot of similarities with SN1. So E2 shares similarities with SN2. That is, it is common only among methyl, primary, and secondary carbon substrates. And just like SN2, attack of the nucleophile and removal of the leaving group, which results in the formation of a double bond, all happens simultaneously. As we look at the E2 mechanism, it'll make sense. But what I'm saying here is, just like SN2, E2 reactions do not have a two-step process. It's a one-step process. That means everything happens all at the same time. Okay, second order. That is, it depends on the rate. The rate of the E2 reaction depends on the concentration of both the reactant and the nucleophile, right? E1, I don't want to go through, shares a lot of similarities with SN1. Now, if you're curious, go back to SN1 and write down what are the things we've said about SN1. That is, it's a two-step process. Reaction rate depends only on the concentration of the reactant and not the nucleophile, and it's first-order reaction, right? And it's predominantly only common with tertiary carbon substrates. Those are things we said about an SN1, and they all apply to an E1 as well, right? Let's understand something before we move further. Now, why did I want to bring this here? Because what I'm going to say right now, really quick in the next few seconds, is something that would probably travel with you for the remainder of the course. So I don't want to keep coming back and reintroduce this concept, but I expect you understand it and remember it for the remainder of the course. Okay, so what is an alpha, beta, and gamma hydrogen? Okay, now you determine an hydrogen is alpha, beta, or gamma with respect to the carbon that contains the functional group, which in this case is the leaving group, right? So if you look at this molecule here, you have a carbon that contains the Br, right? That's your functional group or the leaving group. So in this case, I constructed this particular molecule because it gives the best of both worlds, okay? So the carbon containing the Br, on either side, you have two carbons, right? Each containing two hydrogens. The carbon that is adjacent to the carbon containing the leaving group, in this case, the leaving group happens to be the middle, so you have carbons on either side. So either way, it's the carbon that's adjacent or immediately next to the carbon containing the leaving group contains the alpha hydrogen. You can see that. And the carbon adjacent to the carbon containing the alpha hydrogen is obviously the beta. And the carbon containing a hydrogen that is adjacent to a carbon containing a beta hydrogen is gamma, right? So now say if the Br was on the end, then your alpha, beta, gamma will be all only one direction. Because the Br is in the middle, you have alpha on both sides, beta on both sides, gamma on both sides. Now say if your Br is at the very end of the chain, then you can only go alpha, beta, gamma on one side. But the key, what you have to understand is the carbon that contains the hydrogen that is immediately adjacent to the carbon containing a functional group. In this case, the functional group is the Br, which happens to be our leaving group, right? So the carbon that's immediately adjacent to the carbon containing the functional group or the leaving group is your alpha, and the one adjacent to that is beta, and the one adjacent to the beta is your gamma. right? Let's understand this, okay? So here's your E2 mechanism. So you have your carbon containing the functional group, which is your Br. It contains two hydrogens. So it's a primary carbon substrate, right? So when it reacts with the nucleophile, right, it abstracts the alpha. Remember, it's the carbon containing the Br is your functional group carbon, and the carbon adjacent to the carbon is the alpha carbon, or it contains the alpha hydrogen, right? So the OH minus comes and grabs, which is your nucleophile, comes and grabs the hydrogen, and in the process that bond gets shifted in between the two carbon as a double bond, and in the process the Br comes out, right? You see, this is a simultaneous reaction. The OH minus grabs the hydrogen, and the bond between the hydrogen and the carbon gets shifted between the two carbons as a double bond, and the Br comes out in the process. This is very similar to an SN2, where the nucleophile attacks the carbon and the Br comes out all at the same time. Okay, so this is an E2 mechanism. Okay, E1 mechanism, I'm going to go put it all in here so it makes sense. Okay, so now again, the carbon containing the leaving group does not contain any hydrogens, right? It contains 3 bonds and none of them is a hydrogen. So that means it has to be a tertiary carbon substrate. Now we determine whether a carbon substrate is primary, secondary, tertiary, or methyl has to do with the carbon that actually contains the leaving group. The carbon that contains the leaving group does not contain any hydrogens, which in this case is the Br and 2 CH3s. So that's a tertiary carbon substrate. So it qualifies for an E1 elimination. So as with the SN1, the Br comes off first, leaving a, what do we call this? This is a carbon containing 3 bonds and none of them is a hydrogen and a positive charge. So what did we call that? A tertiary carbocation. So in an E1 mechanism, the leaving group comes off first, just like an SN1, leaving a carbocation. Now you see your nucleophile comes and grabs the alpha hydrogen, and then the bond comes back between the two carbons. Whenever a bond comes, the positive charge gets eliminated, and there you have it. So SN-E2 is all happening in one step, okay? And it is common with primary, methyl, or secondary carbon substrates, and E1 is very much common only among tertiary carbon substrates, okay? Now what I have here is a reaction which contains, basically you have a carbon that's attached to a Br, and then it reacts with the nucleophile, right? So what are the 3 places we can remove a hydrogen? So the carbon containing the Br, and then you have 3 carbons on 3 sides, right? Let's look at those. So you have carbon, carbon, carbon. You have 3 carbons on 3 different directions. All of them can lose 1 hydrogen in the process to make a double bond, right? Now, what type of carbon substrate is this? Well, the carbon that contains the Br contains a metal, and the CH2, CH3 group. So it does not contain a hydrogen. So it can only go through an E1 elimination, right? So this molecule first loses the leaving group, results in the formation of a positive charge. Now keep in mind, an open-ended carbon is a methyl group, right? So this carbon on the left side is a methyl. The one facing down is also a methyl. It contains 3 hydrogens, and then the other one is a CH2, right? So when a nucleophile comes, okay, it has 3 opportunities, 3 avenues to take 1 hydrogen. Now, just because there's 3 hydrogens, they're identical. The nucleophile can pick 1 out of the 3 for each carbon. So, and then it doesn't have a preference for a particular hydrogen in a carbon. It can pick either one of the 3. So I'm going to choose to explain one. So In this case, the nucleophile attacks the hydrogen, and then the bond gets shifted between the two carbons, and in the process eliminates the eliminates the positive charge, right? So you could do that for the remainder of the two carbons. Now you cannot remove all three hydrogens per carbon. You can only remove one, right? So in that case, for the example I've explained, compound A is possible. You can also remove the hydrogen from the carbon facing down, which would lead you to compound B, or you can also remove the hydrogen from the carbon to the far right, indicated by the arrow, and in that case, you would lead to the formation of C. Now, we have three products, and now which one of this would be the most stable? Remember the Zaitsev rule from Chem 330? More centered the double bond, more stable the compound, right? Well, it's very obvious that your C is where the double bond is more centered, and then A, and then B, right? Now, I want you to take the time to understand what is really happening here, right? So first thing you got to do is, whenever you're given a nucleophile and a reactant, figure out, I would specifically tell you whether I want you to do a substitution or elimination. However, I will not tell you whether I want you to do an SN2 or SN1. You would have to decide that based on the carbon substrate. So let's say in this case that you're looking at, I want you to do an elimination, and I give you this reactant and the nucleophile. You would have to decide whether it will go through an E2 or E1, right? Now, right away, you know that the carbon containing the leaving group, which is the Br, happens to be a tertiary carbon because it doesn't contain any hydrogens. So it would have to go through E1. So the leaving group has to first come off, leading to the formation of a tertiary carbocation. From there, typically you have, in this case, you happen to have three alpha hydrogens, right? The carbon containing the positive charge, you have three carbons to the adjacent, they're all alpha hydrogens, right? So you can potentially remove any of the three alpha hydrogens from each of the carbons, which leads to three different products. Typically, if your Br is on the end, then it's never going to be, it's not going to first go through E1, it has to go through E2. So where your Br is located normally controls it, but in this case, I chose to only explain how I got product A. You could have used the CH3CH2O minus to the hydrogen facing below on the carbon that's facing down. You could remove one, and then it would have resulted in product B, or you could have used the far two hydrogens on the right side. Only one of them, okay? You cannot use both hydrogens. You can only use one of them, which in that case would result to the formation of the product C. And if you have to determine which one of these would be a major product, you apply Zaitsev's rules, which is more centered the double bond, more stable the compound. All right, so this is where I want to stop the video for the SN2, SN1, E1, and E2. Let's first get through this idea first and understand what's really happening before we go to E1CB. And there are a couple of resonance structures based concepts I want to look into as we are discussing the idea of carbocation. But those are videos to come. But currently I will have these 4 videos up on our course site, and you'll be able to see them. All right, so stay tuned for more videos.